So we have a piston cylinder assembly, and it contains 1 kilogram of argon. Tell me, what do you know about argon? When you see argon, what do you think about?
Welding.
Welding, okay. Argon comes in bottles and is used as cover gas. Why is it used as a cover gas in welding? Because it's inert. What other inert gases are there? But what does it, hold it, let me back up. Helium is one, but what is really the key idea between helium and argon making it inert? It's what?
They're all in the same.
They're along this, at the periodic chart, they're along the same column. Meaning, well, they definitely are an ideal gas. Okay, I'm looking for one other word that I haven't got yet. It's what? Noble, right? They're non-reacting. That's what it means by inert. They like to be by themselves. They're loners. They're not like oxygen, wants to be paired up all the time with another O, or nitrogen paired up with all the time with another N, right? They're loners. So they're what we call monoatomic. They float around by themselves. And when they float around by themselves, they don't have a lot of energy on the molecular level in the terms of vibrational or rotational modes. Their kinetic energy on a molecule level is all in the translational. They're the best ideal gases.
Because the specific
Heats are constant. The C-specific heats are constant because you really have only one mode of energy storage. So this is really important. So what you want to do is whenever you see argon or helium or other gases that are monoatomic, you can go to the textbook and you'll find the relationship like C sub P bar divided by R bar is 5/2, meaning we know R bar is constant. That means the specific heat is constant. So we can write that as take away the bar, C sub P over R. And so you can get a value for the specific heat if you need it. It's just going to be R times 5/2. What is R? R bar divided by the molar mass. You look up the molar mass, it's around 40 for argon. And we get R 0.20816 kilojoules per kilogram Kelvin. We can calculate then, multiply by 5/2, get the specific heat. Constant pressure, 0.52041 kilojoules per kilogram Kelvin. And if I need C sub V, how do I find C sub V? How do I find C sub V? You can spend a lot of time looking for C sub P for argon in this textbook. You won't find it. You have to uncover it like I'm showing you. Okay? How do you find C sub V? C sub P minus R. There's a relationship between the properties. And so I can get that the C sub V is 0.31224 kilojoules per kilogram Kelvin. Also, what about K? K, ratio of C sub P over C sub V? Cp over Cv. And so when you work through, you find that that's 5/3 or 1.66666666 blah, 1.667, something like that. 5/3. So that should jump out. You should be able to recall, okay, I have an ideal gas, argon, and I know a lot of its properties or can get them. What happens if it's not argon but helium? Change M, same equations work. Okay? All right. It's initially at some temperature and pressure, and it's in a piston cylinder apparatus, and it expands isothermally to a final pressure of 2 bars. So you might want to think, okay, it's in this piston cylinder here, state 1, and then it's going to go to some state 2. It's expanded, true. While it's expanding, it's going to remain isothermal, remaining at 40 degrees C. So let's list some properties like T1 is 40 degrees C, P1 is 12 bar, T2 is 40 degrees C because it's isothermal, it's constant temperature expansion, and P2 is 2 bar. True? Now, how does it remain at constant temperature as it expands? How can that be achieved? Impossible. This is only a textbook problem. No, it's challenging to do it, but you can do it. How would you do it? Dump in heat. There's a heat transfer, Q going in. Because as the gas expands, it's doing work pushing back the base of the piston. That work's coming at the expense of the internal energy of the system. The temperature is going to drop if it's adiabatic. But to keep the temperature up, you bring in heat. The pressure is still dropping during that process. It's an expansion process. For argon as the system, so we just have, like, this is our system at a final state. This is the system at the initial state. What is the work transfer calculated in kilojoules? Well, the work you can do a couple ways. You can think work, I can calculate it from first principles, integral PDV. Sometimes that's most convenient. Sometimes you infer the work by an energy balance where you know the change in U and you know the Q. But we don't know the Q, that's the question for part B. So you struggle a little bit and you think, I'm going to have to calculate this work from first principles, FDX or PDV. So integral PDV, the pressure is not constant, it's falling. But we always know that argon behaving as an ideal gas. What about PV equal to mRT? Is that true? So we can substitute the mRT over V dV. True? And the m, the mass is not changing. The gas constant R is not changing. And the temperature from this problem is not changing. So all three can come outside the integral. We're left with the work equal to mRT. The integral of 1 over V dV, natural log. So we have the natural log. We evaluate at the limits, going from initial state 1 to final state 2, V2 over V1. So, okay, how do I calculate some of these properties? Well, the mass is known, true? The mass was 1 kilogram, written right here. I would encourage you, you can do it this way. Go ahead and calculate V1. What is the volume at state 1? And you calculate V1 by mRT1 over P1. It's just the ideal gas equation used to calculate the volume 1. If we calculate the volume 1, it's 0.054295 meter cubed, and calculate volume 2 the same way. It's 0.32577 meters cubed. Does that volume number, do they look reasonable? Did it expand? It expanded. And by the way, if you want to, you can go ahead and calculate V0, the dead state, because it's still under 2 bar pressure and it's still fairly warm at 40 degrees C. If you take that all the way to 20 degrees C, the dead state temperature, and 1 bar, that'll be even a larger volume, and V0 in the case there is 0.60991 meters cubed. Okay, calculated our volumes. Once we know our volumes, go back to this work, and we can calculate the work done in the process, 1 to 2, and it's a positive 116.7 kilojoules. That's the answer for part A. I'm going to try and put as much of this work on the screen, but I'm going to have to scroll down in a minute, sorry. Okay, so that's part A. What about part B? How do I calculate the heat transfer? You ask the same type of question. Should I calculate it from first principles or deduce it from an energy balance, the first law? Well, we don't know really how to do it from first principles. You have a whole class in heat transfer, 4313. It's on your agenda, right? It's in the degree program. But most of the time, when you want to calculate Q, you do it by calculating work and changes in energy using energy balance. So if we go to the first law, energy balance, we have that U2 minus U1 is equal to what I want to calculate, Q1 to 2, minus work 1 to 2. Is that a good first law for our process? Good. So what we want to do is we want to calculate. Now, what about the left-hand side, U2 minus U1? It's information out of chapter 3. It's ideal gas. There's a couple things you recall about ideal gas. PV is equal to MRT. U is a function of temperature only, and enthalpy is a function of temperature only. All right, so if U is a function of temperature only, and T1 is equal to T2, what is U2 minus U1? It's exactly 0. But you have to do some thoughts. You have to process that to make that deduction. Now we can see, look at Q1 to 2 is just W1 to 2, isn't it, from the energy balance? And so when we solve Q1 to 2, it's the same 116.7 kilojoules. This is a good review of Thermo 1. Everything up to this point didn't require any exergy, any new material out of Thermo 2. But now it says calculate the exergy change of the argon in units of kilojoules. Well, exploit or recall that exergy is a property and just calculate it from that long equation for E2 minus E1 is equal to M times the change in U plus P naught. Well, let me put lowercase v2 minus v1 minus T naught S2 minus S1. And I'm going to neglect the kinetic energy changes and the potential energy changes because I'm running out of room. But I would put them in and strike them because there's no information about a kinetic or potential energy. True? Okay, now, what about this U2 and U1? Is that 0? Sure is. It's isothermal. So you can write it probably a little easier because we calculated these cap V's as being P naught V2 minus V1, where that's the total volume because we calculated them. That's that mass times specific volume. Minus the mass times temperature T naught. Now, how do I calculate S2 minus S1 for a monoatomic ideal gas with constant specific heats? There's some equations, and it's a good review of Thermo 1. It's C sub P natural log of T2 over T1 minus R natural log of P2 over P1. How many people remember vaguely that equation? Good. Good, right? So now, I'm glad that I did get that value of C sub P. Hey, I needed it. Right? And I'm glad I got the value of R. Hey, we needed that. And we can just put in our values for all of the parameters. We got the calculated V's. Just a few notes so that you don't trip up. Put in P naught in kilopascal. And remember that 1 meter cubed times a kilopascal is equal to 1 kilojoule for unit conversion. True? And when you put this temperature in T naught right there, that's at dead state temperature. Don't put in numeric value of 20. Must be absolute, 293 Kelvin. True? The rest of it should be straightforward. And you can calculate the change in the exergy, E2 minus E1, is equal to negative 82.1 kilojoules. What? Maybe we should have paused. If I look at the magnitude and the sign for the answer to part A, does that seem reasonable, 160? Yes, it does. It's doing work, pushing back the piston. It's work out of the argon. How about Q? The Q is 160. That's a positive Q into the argon to keep it warm, to keep it at 40, to make it isothermal during the expansion. But let me get to this. But how about this delta E? Why is that negative? Does the argon have a greater capacity to do work at the end of the process or not? It has less of a capacity to do useful work at the end of the process because it's at a lower pressure. It used to be at 12 bar. It's ready to do a lot, or 12 bar. Now it's only at 2 bar. It's expanded. See, that's why it's a negative change in the potential to do useful work. Okay. Yeah, I kind of put this as a cap V right here. And because I had already calculated those cap V's, and that's why I felt bad doing that, because I distributed the mass one place, but not the other. Okay, I mean, I distributed both places, but I left the mass clearly in one place and not the other. So, okay, because that V2 is right here, and that V1 is right here. Thank you. All right, now let's go to part D. What is the exergy transfer accompanying the work? Well, the total work was so much. All you have to do to calculate the exergy transfer with the work is to get the useful part of that work. Because that's what the exergy is, it's useful. So we subtract off the work, 1 to 2, minus P naught V2 minus V1. Isn't that what you do? You subtract off pushing back the boundary, the environment, pushing back the environment, okay? If you do that, we subtract off around 27. So we find that the useful, the exergy transfer accompanying the work is an actual 89.6 kilojoules. That's the amount of work that could have been used to lift a weight in a gravitational field. The 27 or so kilojoules that is pushing back the atmosphere is not useful. Okay, how about the exergy transfer accompanying the heat transfer? 2 ways you can think about it. I go back and calculate this from either first principles, the integral 1 minus T naught over T times del Q, or I use an exergy balance. In this case, I look at that and I say, is T, I have T naught, that's constant, but is T staying constant during this process? This is one of these rare cases where you can calculate this integral, because that integrand is it's just 1 minus T naught over T, and now you have the integral del Q, that's just Q. And we already calculated the heat transfer. So it's as if this heat transfer, going through some Carnot cycle efficiency, and here I have to scroll down, I'm very sorry about that, but EQ is equal to 1 minus the dead state temperature, 293, divided by the 40 degrees C, you add 273, that's 313 Kelvin, right? Make sure they're in Kelvin, those temperatures, multiplied by the Q, which is 116. I'll just leave it like that. And so you find the exergy transfer with the heat transfer is only 7.5 kilojoules. The heat is coming in only at 40 degrees. That's not a very high temperature. It doesn't have a lot of potential to do useful work. It's just keeping the argon warm. So even though there's a lot of heat being transferred, a lot of energy being transferred with the heat, there's only a little potential to do work being transferred with that same Q. It's only 7.5. That's a dramatic reduction, isn't it? From 117 to 7.5. Now, what about the exergy destruction? Well, this time we will use our exergy balance equation. Let me try and put it over here. Our exergy balance equation is, we have the change in the exergy. Hey, we already calculated that. That's negative 82.1. Is equal to the exergy transfer coming in with the heat. We just calculated that. It's a positive 7.5. minus the exergy being transferred out with the work transfer. We just calculated that. That's a positive 89.6. Minus the only thing we don't know in this equation is that exergy destruction. And when we calculate that exergy destruction, we find that it's a whopping 0. Oh, hold it. How is that? How can I calculate the exergy destruction being 0? It just means something about the process. What does it mean about the process? It's reversible. There are no irreversibilities, at least in this model. True? So we find that there's no exergy destruction for this problem. Any comments or questions?
So those equations that you use for the CB and CP,
Yes.
do those equations, like, I mean, I've never seen them before, that's why.
Oh, you should have. And you need to make sure they're all on the equation sheets, and if you need to, we can go.
No, I'm talking about the CP is equal to R5/2.
Oh, that's in the appendice. And so go to the table A20. Go to table A21. So to find out this result right here, that's in the bottom of table A21. Yeah, you almost need to know where that information is. It's the bottom line. It says monoatomic gases. Hey, what's a monoatomic gas? Is argon a monoatomic gas? It sure is. How about helium? Sure is. Do they give you a list of them? Oh, they even tell you neon is one too. So they just explicitly list with that footnote helium, neon, and argon.